Okay, so what we're going to explore is the law of conservation of mechanical energy. Conservation means staying the same. So this is the mechanical energy stays the same. Now this is for isolated systems. So isolated meaning that no energy is exchanged back and forth. So anyways, let's just get into it. There's many types of energy, including mechanical, nuclear, electrical, light, kinetic, etc., blah, blah, blah. But they all fall into the general category of either kinetic energy or potential energy. Now, mechanical energy, as we just have stated recently, is the sum of all kinetic and potential energy that is contained within the system at a particular point in time. Now remember that that's kind of the key, is that it's just at one point in time. It's not an overall thing, it's at one point in time. So as Kim mentioned, EM is equal to EK plus EP. EM is our mechanical, EK is our kinetic, and EP is our potential. So the law of conservation of energy states that an isolated system, in an isolated system, the mechanical energy of an object remains constant. Okay? Remains constant, meaning it's conserved, right? That's the whole thing, law of conservation, keeping it the same. Of the object changes position. The kinetic and potential energies are just converted from one to the other. So if I have that potential energy, now it gets converted into kinetic and it can go back and forth. So an isolated system is a situation where neither energy nor matter can enter or leave the system. So that means, like, we can't have frictional force happening. So this is almost basically mostly imaginary, right? There's nothing that's really actually completely isolated, because we'll have generally the force of friction or thermal energy losses and things like that. So this is kind of a hypothetical thing that we use to make calculations easier. Okay, so we disregard force of friction for these types of questions. Okay, so when we think of, let's represent this graphically. So put energy on this side, and that's always in joules. And put position on the bottom. So that just means like different points in time. So say we're at position A, and then we're at position B. So say with position A, it's all like potential energy, okay? So my red is going to be EP, and as I go to position B, my EP goes down. So this is potential energy. So that energy, I started with a lot of potential energy, and it went down. But I'm saying that this is an isolated system, so it doesn't just disappear. It needs to become something else. What else would it become or be converted into? What type of energy? Kinetic energy. So now let's draw a blue line showing our kinetic energy. So this is like our EK starting out at the bottom. And at point B, now I have all EK. Now this green line is going to represent EM. So at the beginning, at point A, let's say point A, all EM equaled EP. There was no EK at the very beginning. And this is just for like say a pendulum that I'm holding up and then I let it go. So it has all potential energy and then it's all converted into that kinetic. And then here at say this hypothetical point B, all EM is equal to EK. So one is converted into the other. So let's look at some more like tangible examples next. So you can flip to the next page.